So in about 1 minute, we will start our interview with legendary stratigrapher Professor Frits Hilgen. And Frits has spent the vast majority of his career doing what's called cyclostratigraphy. So stratigraphy is essentially the science of rock strata, rock layers. And cyclostratigraphy is a type of stratigraphy whereby you focus on cyclic changes in Earth's climate. So these cyclic changes, they are pervasive throughout the history of the Earth. So they've basically happened since the Earth formed. And they are caused by the gravitational interactions between the Earth and the Moon, as well as the gravitational interactions between the Earth and the other planets in the solar system. So because these are astronomical interactions, they are extremely predictable. And using computers and various physical analyses, you can actually reconstruct exactly how these changes have occurred throughout the Earth's past. Now, basically, to get a sense of what Frits actually does in his work and how it contributes to our understanding, is that he looks at these various astronomical cycles. So we have the precession cycle, the rotation of Earth's axis, the obliquity cycle, the change in the tilt of Earth's axis, and the various eccentricity cycles, which are changes in the roundness of Earth's orbit. And all of these have very unique characteristic periods that then affect the amount of sunlight that reaches the Earth. So this is called insolation. So using analytical tools, you're able to reconstruct the insolation curve, so the change in how much sunlight reaches the Earth. And that obviously affects the climate. So these climate changes are then recorded in the stratigraphic record, right, in the record of rock layers. And the cyclostratigrapher goes out into the field, goes out into the desert or wherever these layers are exposed. And he maps and analyzes these cyclic stratigraphic changes and then uses it to construct this very well-known chronostratigraphic chart of the various geological time periods. So anyone who's ever had anything to do with geology has probably seen this chart. It shows all the various geological time periods, and the exact timing of these periods are partially determined by these types of techniques. Right, so obviously you also use other types of stratigraphic techniques like magnetostratigraphy, which uses Earth's magnetic field, or biostratigraphy, which makes use of fossils and extinctions in these fossils. So if you combine all these stratigraphic sciences, you're actually able to determine exactly what has happened in the Earth and exactly when these changes occurred. So this is extremely complicated material, so hopefully this tiny introduction helps you a little bit understanding what the interview is about. But it is also very, very, very important in our understanding of the Earth. So Frits is really a wealth of information when it comes to this type of science. So I really hope you enjoy the interview and that you learn a little bit about stratigraphy. So I'm here with Yente, who is also going to ask Frits some questions. As a first question, Frits, how did your career start? Like, did you grow up thinking, I'm going to be a cyclostratigrapher? Like, I suppose you didn't, but how did this happen?
Now, maybe the first question to answer is how I started to study earth sciences. Yeah. It's a more general question. And so I'm coming from the east, so maybe you can still hear that from my accent. And then in the beautiful, most beautiful part of the country, Twente, you can find these fossils. And when I was a kind of 10 years old, I found one of these fossils, and then I didn't know what it was. It looked like a dried out orange. And in the afternoon, I went with my father to this beautiful small museum, Natura Dozet, and then it was in one of their boxes, and it was called Aulocopium aurantium, so it was an Ordovician sponge of 350 million years old, and it was transported to the Netherlands by the ice 150,000 years ago. So I think that is actually the trigger of why I started to study earth sciences, and maybe also my fascination, not so much about cyclostratigraphy, but about time, geological time. And so then the other question is more into the cyclostratigraphy. So that is a bit of strange story, because my career doesn't look like very exciting. I started my study in Utrecht in 1976, so when we are still at the old institute, Geological Institute, at the Ouwegracht 320. We moved 2 years later to the Uithof. And so I did my bachelor, what we call now bachelor and master there. I started my PhD, did my postdocs, and then become a staff member just only in Utrecht. So that sounds a bit, not very exciting. But the reason for that was that we had a very good, I think one of the best teams in the world to study these cycles with integrated stratigraphy. But the nice story is more about my PhD, because I started on a totally different subject. So the subject of it was a proposal for NWO. Didn't make it the first year, so I spent 1 year on working on my PhD thesis without getting money. And then the second year was also rejected. But then NWO said there was some money left, and my promoter, good old Cor Droge, he said, okay, then you have to spend it to the next proposal to fund it. So my proposal, or that of my supervisor, was funded. And I could start getting paid at least.
So it was, So it was necessary for you to actually maintain your funding during your PhD? Is that?
No, once that was accepted, then it was for 4 years.
Okay, yeah.
Yeah, so that was fine. But the beginning was more difficult because the first year was not funded, and it was on a completely different subject. So my original subject was to reconstruct the Pleistocene sedimentary basin history of southern Italy. And yeah, that was nice, but difficult. And then in southern Italy, in Calabria, there was also the team of the Paleomagnetic Lab with Jan-Willem Zachariasse. They were working there on sections which has these very nice regular alternations that I used already for correlations. And actually I became much more fascinated with these cycles than this whole sedimentary basin history. Yeah. So I changed actually the subject of my thesis completely, and against the will of my supervisor. So that is a nice message maybe to PhDs nowadays.
Yeah, that's what they say, right? All the good scientists are rebels. So you're definitely a bit of a rebel in your PhD.
You need to be a bit of a rebel, yeah.
So just a little bit of background for the perhaps not so geologically inclined is that Frits was tasked to reconstruct the geological history of southern Italy. And the rock layers displayed a very regular, nice pattern, which obviously we now know was caused by orbital cycles, Milankovitch cycles. Was this a big topic of study during this time, or is it really your own personal interest that started this exploration?
So it was an interesting time because they started to study the Milankovitch forcing of the ice ages, because they recovered these piston cores from the bottom of the ocean since the 1950s. Okay. So that was underway, but that was only about the Pleistocene ice ages of the last 1 million years. And so then we start to study more the cycles in older parts, and not only related to the ice ages like the subpropels. Yeah. And so I think they started before, but the way we looked at it, so we had this excellent team with magnetostratigraphy from the Paleomagnetic Lab, and we had the biostratigraphy. And so then we started to create what is now known as the astronomical time scale. Yeah, so to explain that a little bit, you have these very nice cycles that you see in the field, that you see in the parameters that you measure. And then you can also calculate curves, what we call target curves, from astronomical solutions of the solar system. And these curves are then of the precession, obliquity, and eccentricity cycles. So we can correlate the cycles that we see in the field to these astronomical cycles, and then you get astronomical ages. So these are numerical absolute ages. So that was really a revolution, because we extended what we call the astronomical time scale from the last 500,000 years to the last 5 million years. And the nice thing was that the astronomical ages were up to 10 to 15% older than the existing argon-argon and potassium-argon ages. So the geochronologists were not happy with that. They didn't believe the astronomical ages. But that was solved because the progress in argon-argon dating removed that discrepancy soon.
Yeah, that's very cool. So basically you're exploiting the regular motions of the planets in the solar system to very accurately reconstruct the history of the Earth, essentially, right?
The history of the climate, how the climate system reacts to the changes in the insolation.
Yeah, because what you're really looking at is climate change, right? You're looking at changes in climate because of changes in the...
Just to explain that a little bit more, so you have these, what they call the Earth's orbital variations, so the changes in the shape of the Earth's orbit and in the rotational axis, the tilt and the rotation of the axis. And so these three parameters, they create changes in the insolation that we receive on Earth. And so that's not so much the annual insolation, but it's the seasonal insolation. So if you look at these curves that you can calculate, so you have the astronomical solution nowadays on your laptop or on internet, you ask, I want to create that insolation curve, 30 degrees northern latitude, summer insolation for the last 5 million years. You push on the button and you have that curve. But the main thing is that if you look at the amount of change is, let's say, up to 25-30%. So a 30% increase in summer insolation will definitely affect a climate system like the monsoon. And so that was not always realized at that time, but these seasonal changes are really, really very large.
Just wanted to ask, so just to confirm, are you saying that this isn't an annual thing, it's seasonal?
Yeah, so the periods of these cycles are 20,000 years for precession, 40,000 years for obliquity, and then eccentricity, mainly 100 and 400,000 years. But they affect mainly the seasonal changes in insolation. So not so much the annual, it's the seasonal changes. And that is controlling climate.
It's incredibly fascinating, right? Because basically, when you just started this research, your career basically, it was really underexplored in that sense, right? These super accurate astronomical ages that we now take for granted only existed for the very recent sediments. Is that correct, or?
Yeah, so basically the astronomical solutions for the solar system at that time were only accurate for the last 1 million years. So I remember the times that we got new solutions and then they fitted and then they didn't fit anymore and then they fitted again. So that was really exciting times. But since then the astronomical solutions have improved considerably. But you have to realize that all these changes have been recorded in the sediments as these nice cycles. And so then you can go actually, one of the problems with the astronomical solution, for instance, is what we call the chaotic behavior of the solar system. And so you know the chaotic behavior that's why weather is so very difficult to predict. And the sensitivity to initial conditions. So at a certain moment, beyond 50 million years, you don't know anymore what solution is reliable. So then what the astronomers can do, they generate maybe 10 or 20 or maybe even more solutions with very small changes in the beginning. They calculate all these solutions and then they can see what solution has the best fit with our data.
Wow.
And that is then probably the solution that is the most reliable. So that is really exciting, and so that are the more recent developments, and that's nice.
I could imagine that taking those solutions provides a lot of trial and error situations. How did you cope with actually all your errors? Like, what did you do to make it fun?
Yeah, so to remove the errors is, let's say, we apply what we call integrated stratigraphy. And so you apply all the different stratigraphic methods because you need an initial age model for the cycles that is as good as possible. So the initial age model is then based on the combination of magnetostratigraphy and biostratigraphy or radioisotopic dating. And once you have that initial age model, then you can start this kind of what we call the tuning exercise. To correlate the cycles to the astronomical target curves. But it really depends...
So basically linking the rocks with...
It really depends on the accuracy of your initial age model. And that's also the fun, so that's what I like very much. It's really interdisciplinary. So you also have to bring together, for instance, the astronomical dating community with the argon-argon and uranium-lead dating community. Because let's say if our standard geological time scale is based for the main part on these three methods. So if you date the same event, you should in principle arrive at the same age. But that was not always the case. So that's another issue we are working on. So that are the nice issues. You can work on these for basically decades because you solve them step by step. It takes a long time. And that's one of the things we are still working on, but we are getting very, very close, I would say.
Yeah, so that's very exciting, right? So you're basically, this technique starts out as a tool to very accurately date the rock layers, but you've now extended it towards being able to actually essentially do the opposite, which is say something about the solar system from the rocks. Is that a correct description? Or?
Yeah, that is certainly a correct description. So the most recent developments, it started also a bit earlier, but you can use the cycles because it has been recorded to, let's say, reconstruct these chaotic transitions in the solar system. You can use it to reconstruct the Earth-Moon distance.
Oh, wow.
And that's quite amazing. So that's also what I liked during my career with the entire team we worked with, that sometimes we really switched. We always studied Milankovitch cycles, but we started, let's say, with the last 15 million years. Then we had the deep marine of the Mediterranean with all the subpropels. Then we moved to the continental successions. Then we moved to the fluvial successions in North America. And the last 10 years I moved also to the Precambrian because not much was known about Milankovitch cycles in this very old part of the geological history. And so that's a very nice story because I worked there with two PhDs. Bianca is still working on the Ediacaran, but Margriet, she finished already with the banded iron formations of 2.5 billion years ago.
Wow.
And then you work there in northwestern Australia in Karijini National Park and you go down in these beautiful gorges and then you see these cycles and then you think, whoa, how is it possible? And then you can use these cycles not only to reconstruct the Earth-Moon distance, but also these are redox cycles. So redox cyclicity, so how does it work? And actually Margriet, her idea is that it actually produces oxygen. So these Milankovitch cycles may play, actually I think, a crucial role in the production of oxygen in the Earth system.
How does that mechanism work?
So basically it's all very robust. So the subpropels, these dark layers in the Mediterranean, they have been related to intensification of the North African monsoon. But once you have continents, the monsoonal system will be there. It will also be already before. But so also these cycles in the banded iron formation are likely related to the monsoon. And so you bring in, if you have enhanced rain, you bring in more nutrients and then you have these cyanobacteria that start to bloom. And cyanobacteria, they produce oxygen. So you can ask, so I asked myself the question, let's say, what would have happened if Earth's orbit would have been circular? Then I guess we would not be sitting here because then maybe not much oxygen had been produced. So
okay, so it's the changes that is forcing this oxygen cycle?
So the monsoon is influencing that because it depends on the productivity of the cyanobacteria, how much oxygen is produced. And it has then to escape to the atmosphere.
Sorry, Frits, you just mentioned that you've studied the distance between the moon and the Earth, and you mentioned different geological ages. Has there been any major variation that you can think of?
So that's a very interesting study because Margriet works on that with these very old rocks. And the basic approach is that the eccentricity periods remain essentially stable, constant, not really, but you can assume. And the precession and obliquity cycles become shorter in period, back in time. Because at that time then the Earth-Moon distance was shorter, and that affects the periods of obliquity and precession, but not of eccentricity. So you just have, what you have to do is if you know the ratio between your eccentricity-related cycles and the precession or obliquity-related cycles, you can convert that into the Earth-Moon distance. So the nice story was that Margriet was working on that, and that Jacques Lascar had a PhD, Mohamed Farad. He was working on the modeling. And so the models went back to the 80s and they could be improved. So his model was better. And then he got the data point of Magritte. And to his surprise, the data point at 2.5 billion years ago plotted exactly on his modeling line.
Really?
So that was really a whoa, that makes sense.
So this is essentially an unprecedented look in the very, very early solar system, because there's no really any other ways to get an observation of what the very early solar system looked like, as far as I know.
No, so the only two approaches that you have is modeling and looking at these Milankovitch cycles. You have, let's say, you can use tidal rhythmites.
Oh, okay.
But that's difficult because, in the nodes, it's very difficult to count the number of tidal rhythmites.
And that's also not related to the planets, right?
No, but it's related to the Earth-Moon system. You can actually use that to calculate the Earth-Moon distance. And so there are some very nice examples of that, but that is rather limited. And you can use fossils like corals if you know the number of daily growth bands in a year. But that's also not so easy because also the number of days in a year will change, and that is related to the Earth-Moon distance. But it's very difficult to count that number of growth increments in an annual cycle of a fossil. And so the idea now is that this third approach of the Milankovitch cycles is the best approach, the way to go.
Yeah, cool. So is there anything like specific you can say about this early solar system? Do you think there have been any major rearrangements? I know there are some theories out there in the astronomy field that there's perhaps a 9th planet out there in the distant solar system. Can you basically disprove those ideas with this technique?
I think that these kind of influences are basically too small to be registered. That will be within the noise. Yeah. And also we don't have, let's say if you go further back in time, you really need to solve these kind of issues. You need excellent records. And they become more rare if you go further back in time. And so we would love to have records of 3-4 billion years old, but they are simply not there. So there is a limit to what we can do, but I think already we can do quite something. So things as, let's say, the what they call the early bombardment of the inner solar system, that's beyond our reach, I would say.
Okay, yeah.
Well, personally, I would love to go on fieldwork again. I don't know how it's for you, but I've heard great stories about it. But how do you exactly find those locations that you want? Do you just choose the place you want to go to, like, which is the nicest sun? Or do you actually have some preparations you need to do for that?
Yeah, the story is that we select our fieldwork areas based on the quality of the wines and the nice weather. But then somehow it always coincides with the exciting rock records. So
is the quality of the wine also related to the Earth-Moon system, or is that?
I'm not sure. But the wine does not exist long enough to prove that. But the fieldwork is, let's say, that's also what I like. Fieldwork is a very important aspect of the work we do. And so I am more a fieldwork geologist, but other people in our group, like Luc, for instance, and Matt, they work more with the course taken by the drill ship, the international drill ship, the Global Challenger. But I am a field geologist, and I like field geology, and also because I realize how important it is. But it's also a kind of, let's say, way of life. And like the old naturalist, you like to go and hike and try to understand what you see. And so it's basically you do the same, but on the ship is quite different. And that also brings me, let's say one of the questions that you had about the teaching. That's also what I found very important, that during the last 20, 30 years that we managed to keep fieldwork as a main part of the curriculum for our students, because I think it's the basis somehow for the earth sciences.
So just before the interview, Yente and I were actually wondering, how much time have you spent in the field? Are you keeping track, or?
Not in detail. But the estimate is something like 9 years.
9 years in the field.
9 years in the field. So that's the field work with the PhDs for research, but also with the students. And so I've been involved in the first year field work, the 4th year's field work. And I've seen that evolving. And so basically now it changed again with the new curriculum for the bachelor. And probably I'm not that happy with the changes for the first year's fieldwork, because the first year's fieldwork, I've been leading that for 5 or 10 years in Aliaga. That was really the same type of fieldwork that I did as a first year student. So it's called a mapping fieldwork, but mapping is a completely different term for that fieldwork, because you need to map to reconstruct geological history. So the fieldwork is related to reconstructing geological history, so to think in 3 and 4 dimensions. And I think for that purpose, this Aliaga, let's say the old-fashioned mapping fieldwork, is more suitable than the exercises that they developed. Of course, they did their best, and it was unavoidable because it had to do with bringing earth sciences and physical geography even more together. But I don't like the outcome. But maybe I'm old-fashioned.
No, well, I happen to agree with you in that sense, because the real classical fieldwork exercise is the mapping exercise, right? So every geology program has a mapping exercise where you go out and map rocks. You explain it very clearly, like a 4-dimensional view of the world from the rocks, basically. And now, just to give some background, is we've recently changed our bachelor program to be a little bit more interdisciplinary, I suppose. So there's a little bit of river research and some other things, but it goes at the expense of the mapping exercise.
Yeah, but the mapping was, in my idea, is always the wrong term, because it is a fieldwork. So the mapping is the tool, but what you try to achieve is to reconstruct geological history, and that's what we have to learn. And I think that's also what students always appreciated about the Aliaga fieldwork. In the last 2 weeks, they started to see, okay, this is why we do the fieldwork. This is why you log the sections, you make the geological map, but these are the tools, and you use them to reconstruct geological history.
So out of all those 9 years of research in the field, what is the most beautiful outcrop, the most special memories, perhaps also some of the lesser nice things that you experienced?
Yeah, so the nicest. So actually, one of the things that, because I retired last year, but I'm still working, of course, with Bianca's PhD, and also I like it to work with young people. It keeps you sharp, and there are still these unfinished topics, like this Fish Canyon Cenodyne problem, the age of that standard, and so on. So we continue, and I really want to continue to work on that. So the fieldwork, so I'm also, one of my plans is to write a book about beautiful sections on Earth that I studied.
So you can revisit them all over.
No, yeah, so yeah, but we have probably already the pictures, but also but it's for a broader audience.
Yeah.
So what can you do with these rocks? All these alternations that a lot of people have seen them while they were hiking in the mountains. So they have seen these regular alternations, but what do they mean? And to tell that in a book for a broader audience.
Does that book include a wine map?
I have to think about it.
I have heard of places where they put fossils in wine. Maybe you could find something about that. Tell us. I'd love to read about it.
I think also people would be curious to know, in your 9 years, what was the most efficient lunch? If you've done a lot of fieldwork lunches, what's your go-to?
No, so we always lunched in the field. So because, let's say, it doesn't make sense if you go into the field, you walk a long time, and to go out of the field again. There is this story when we start to collaborate with the Spanish colleagues, and we were in the field, and at 12:30 they started to look on their watches. Why are you going to? And so we had to go out of the field because they wanted to have lunch. So we had to drive, I think, 3/4 of an hour to the restaurant. Then we had, for 3 hours, we had a Spanish meal with wine and beer. And then it was 5 o'clock. But then for us, that's fine. Okay, well, you have to go back into the field. But they didn't want to go back into the field anymore. So the next day, we worked there together with a Spanish colleague, Paco, said, okay, we will have just panini in the field, and that's it.
Panini is the answer.
Yeah.
All right, so one of the key things you've been working on is, I guess not just you, but the whole group here in Utrecht, is this event called the Messinian Salinity Crisis. So what can you give like a brief description of what that is, what happened, and also what sort of outstanding questions have you worked on?
I think in that respect you can better interview Wout. He knows more about it. But let's say when Wout was one of my first PhDs, and he started to work also on, let's say, with his postdoc on the Messinian salinity crisis, because the age models at that time were all completely different and wrong. There was not a single age model that was correct. And so we worked already on the older successions with the subpropels for building this astronomical time scale. And so that's then we said, okay, now we have to fill in that missing gap of the Messinian. And so we also looked at, these are also cyclic, the evaporite deposits.
So what exactly happened during the Messinian salinity?
So during the Messinian salinity crisis, you get this, so it's interesting, you get this probably very short phase, so you get a closure of the connection, not a complete closure, because you still have input of Atlantic water, but you don't have outflow, and then you can get concentration very rapidly. And so the basic idea about these astronomical age models that we now created for the Messinian is that this 2.5 kilometer of Messinian salt, so the final stage, that 2.5 kilometer of salt has been deposited in just 50,000 years or something.
Is this the salt I also put down on my bread? Or
I think that can maybe I Twente.
Okay, that's right.
That's even older, right?
Yeah, that is much older. Yeah. So that's the interesting thing. You have more of these Salana giants, what they call, but the Messinian is the most recent one, and it's extremely difficult to understand all the details, because after that phase of the salt deposition, you get these lago mare conditions, more freshwater, brackish water, and it's still not completely clear what happens before the reflooding at the base of the Pliocene. Then you get again normal marine conditions.
I guess you would assume that during time the skills and techniques have developed to discuss and find out those different types of things. Have you noticed anything about that while doing your research?
Yeah, so there's of course a lot of development in the proxies that we use. So the proxies, they are measured to reconstruct certain parameters like temperature or productivity or salinity. And so there is a huge development in these proxies. That's not my thing, but I know, of course, because I apply these proxies. And that makes it interesting, but it's always also with proxies that they are often multi-interpretable, so that makes it not always straightforward. But some of the proxies are very promising, and so for instance, Martin is working on the clumped isotope, so that is a kind of probably the most reliable proxy to reconstruct temperature. And temperature, of course, is one of the parameters that we really want to know to see what happened in the past, and let's say, does it tell us something what will happen in the coming hundreds of years.
But there are no extra other developments to help you figure out what happened in the Messinian?
Yeah, so we worked on the Messinian, let's say, 2000 to 2005, and so we still probably go back there in May, but then I work mainly in North America and in the Precambrian, and so I don't know all the details. So that's why I said, maybe you have to invite Wout for an interview. Then you can discuss the salinity crisis in detail.
Yeah, we certainly will.
Yeah, the next time.
Yeah, so Wout Krijksman is a direct colleague of Frits, and he was your PhD student?
One of my first PhD.
Okay, I didn't know that, but he's a professor here, and he's an expert in magnetostratigraphy. So they're both stratigraphy, cyclostratigraphy and magnetostratigraphy, but you use the cycles, right, which are caused by the planetary interactions, and magnetostratigraphy is based on the reversals in Earth's magnetic field. And it's basically the combination of the two that gives you a really good sense of better age constraints of the past, right?
Yeah, so that's what I called before integrated stratigraphy. That's really the way to go. So you work together with a lot of experts and to get the best possible age model. But let's say also the age model. The age model is just a tool. So we create the best possible age model via this method of astronomical tuning. But the main thing is that what you really try to understand is how this astronomical climate forcing works. So that Margriet studied the redox cycles, and you could see, okay, probably it has to do with the production of oxygen and so on.
Yeah.
And so that is, I think, even the more interesting question. And that was also one of the interesting developments but that was with Nana Weber, who left us way too early. So we included climate modeling of orbital extremes to better understand the astronomical climate forcing, especially of subpropels. Yeah, that was very, very interesting as well. So you see, and that's the nice thing of being a stratigrapher or cyclostratigrapher. You really need a multidisciplinary or interdisciplinary research team to answer these fundamental questions.
So as a cyclostratigrapher, you, if I pronounce that right though, you do the cycling and you do the things over and over again. Like, do you have a special type of field group or like people you want to work with together, like your most fun partners? Are this also in the cyclicity?
So that's what I said when I was a PhD and a postdoc. We had, I think, the best team in the world, I would say, with Wout and Cor from the Paleomagnetic Lab and Jan-Willem Zacharias from the Planktonic Foraminifera. I think there were no other teams in the world who were able to do that job. And then afterwards you change, of course, the composition of the research team depending on the scientific problem that you want to solve. But it's always very important with the research team to have people that you, I would say, that you like. So you should be able to collaborate, and then it's more handy if you like the people.
Yeah, you have found them here.
Yeah. But also we work together with many international scientists.
Yeah, I guess if you're going to be stuck with people in the field for 9 years, you probably have to get along, right? Okay, so far we've talked a lot about the past, right? But it's always good to look at the future as well. So what would you consider to be some sort of gaps in our understanding regarding this field? What are some of the things that you think are going to be a good research pursuit in the coming years?
So that has become more difficult because it has become more a mature science. And let's say it's already looking at all the limits that is possible. So to reconstruct the solar system and Earth-Moon system, it's really trying to get the limits out of the cycles that are there. And also with the proxies, there are a lot of developments. But one of the things that are important, you see these developments working with the proxies, is, for instance, to get this idea of climate sensitivity. So how much the temperature will increase if you double carbon dioxide. And then you have different definitions of climate sensitivity. And I think that it will be one of the main contributions of the type of work that we do as paleoclimatologists. And so then you do not become very happy if you know what comes out of these studies. You will really become worried about the future of children, grandchildren, whatever. And what is happening now in the world.
Yeah, so that's a good jump to climate change. So what, in your perspective, what is the most likely climate sensitivity? And does the paleoclimatological climate sensitivity estimate change markedly from the modeling estimates?
Yeah, so as far as I understand, there are some definitions of climate sensitivity, and the one that is one is that's going more trying to go into equilibrium, the equilibrium sensitivity, that's on longer timescales. But the thing that we learned also from Milankovitch cycles, that you never reach equilibrium because the natural climate system always changes. Yeah. But let's say they can get an idea about this, so that's on the longer term equilibrium climate, and that is climate sensitive, and that is something like the estimates I think are now 6-7 degrees per doubling of carbon dioxide concentration. So that's not, let's say, the short term, let's say up to 2100, but that's centuries.
I had a question. So basically, like, obviously climate change is a big topical issue. I've always wondered if, like, human beings, let's say that people don't change, sadly, and that the climate keeps changing. If we were to go, would the climate adjust itself? Because we've seen major climate shifts in the past, and the Earth seems to correct itself.
Yeah, so the climate system will restore itself, but let's say the uptake of carbon dioxide takes quite some time. So they also modeled that, of course. So the weathering is incapable of removing carbon dioxide from the atmosphere again. But that will take quite some time. But what concerns me most is if you see how mankind is able to change the climate system. So, for instance, the Atlantic meridional overturning is changing, it's collapsing. It's likely to collapse the coming decades. And we are responsible for that. And we don't care. If you look at how we now, with the politicians, how we change the world, we don't care. It's ridiculous, in my opinion.
How would you get people if you could show the everyday person who hasn't gone to university? How would you get them to understand?
I think that's very difficult because what you hear is that people, if you have this message, that people get tired of hearing, and maybe they also don't want to hear these kind of pessimistic future scenarios for mankind and our planet. But I think as we have a responsibility, not so much maybe for the Earth, but at least for our other animals that are living on the planet. So we should somehow take care of that. And if we have a major mass extinction, we are responsible. I think we cannot do that.
What do you think will be like the first step towards decreasing this chance to have stop the meridional overturning?
That will be very difficult. So now with the current political ideas and system in the world, that it's going the wrong way, and it will go faster. And it's very strange that you can have political leaders that just neglect global change, global climate change, does not exist or don't believe in it. I don't know. It's in my opinion, it's how can it be?
Would you then say, like, if you said that the political leaders nowadays don't know that much about the climate change and how it works maybe in a scientific way, would you then say maybe put a team of scientists into, for example, the politics system of each country so they can decide together?
Yeah, so you can ask the question whether the democratic system is capable of solving these issues. Because let's say the classical Greek already knew what the danger was of the democracy if you have a demagogue. And then, yeah, that's exactly what you see what's happening nowadays. And also, let's say, the classical Greek, let's say, it was not a real democracy because not everybody was allowed to vote. They had slaves. But the people that were allowed to vote, they made sure that at least they were relatively well informed when they had to vote. And now with all the fake news and so, that is completely impossible for most of the normal people.
Physicist here, so she actually has some questions for Frits.
So the changes in the meridional overturning circulation, is it also something that you've seen in the field or in other parts of cyclostratigraphy?
So it's very interesting. There are paleoclimatologists working on it, but also climate modelers, of course. And it's clear from the paleoclimatic record of the last 100,000 years that you have. So it's not the Milankovitch cycles, it's on shorter time scales. They have these, what they call the Heinrich events. And then also you have these switches in the overturning circulation, or that say that it is much reduced. So also due to natural causes, this can happen. But what we now see, and it goes very rapid, that we are responsible for it. And the consequences can be enormous. You really change the entire circulation of the oceans.
All right, so I remember from I actually took your course, what was it, like 7 years ago or something like that. And one of the things I vividly remember is that you always include a significant piece on the history of the discovery of all these different things. Why do you do that? Why do you think this history of science is so important?
So there is actually a paper, Hilgen 2010. So it looks like that astronomical tuning, astronomical timescales is something of the last 50 years, but it's not. It goes back to the 19th century, the initial ideas. And so I actually wrote a paper about the real beginning of astronomical tuning. Of course, at the time they didn't know anything about the age of the Earth. There was no radioisotopic dating, nothing. But they already had ideas, they were speculating about, and that makes it so interesting. It's about how these ideas are being developed. And that's also what, let's say, what students I think have to learn, because nowadays what you sometimes see, especially with the master thesis, or also maybe a PhD thesis, that they refer to a paper and then you think, why do they refer to that paper? That is not the initial paper where the idea was published.
Yeah.
And so apparently then they don't care. And I think it's very important that the people that came up first with these ideas, that you refer to these papers.
Yeah.
And so what I learned when I was a student, when I'm a master student, and write my master thesis, which took 2 years.
All the good ones do.
But that was very, very interesting because we were in a room with 5 master students and we worked on piston cores from the Adriatic. And one worked on the benthic foraminifer, one on the planktic foraminifer, one on stable isotopes, one on geochemical elements. And so we all had our own research, but we also had a lot of discussion between us. So that was a very interesting time. But what they learned us, the staff at that time, we always, when we write it, and we have to go to the original literature. And that was not always easy to find. Who was the first one to publish the ideas? How did the ideas develop? And I think that is just a critical part of science, I would say. And that's what also students have to realize. And I realize, of course, a first-year student, they are not interested in that. So I also had it in my second-year course about stratigraphy, but I refused to skip it. Then at least you have to listen to it.
You've actually experienced the real sort of old, what was it, like a 400 or 500-year-old building that's been in use for many centuries. And that was the heart of the geological science in the Netherlands for a while. What's it like to have this link with the past? And what are some of the older people that maybe now the younger generation has forgotten that has actually affected you?
Yeah, so that's interesting. Let's say what I still like are these old-fashioned geological institutes with all the geological maps on the walls, buildings that are hundreds of years old. And now we have these new buildings, and I must say I'm quite happy with this new building. It's spacious and so on. It's nice with all the rooms, separate rooms for discussions and so on. So it's very convenient. But I also still have this feeling it's not the old geological institute.
There's not enough rocks lying around.
No, they have, because that's also not allowed. So I would say that the architect doesn't want it. So I think having a fossil dinosaur at the entrance, that at least makes clear that's a geological institute.
So this is exactly what I've been saying for years. I actually want a skeleton that goes into the atrium with the neck all the way up to the 7th floor.
So in the old building, we had the stairs and the staircase, and then they had these copies of the paintings by, I think, a Hungarian painter. So, and it started with the Precambrian, the Cambrian, with all the animals and so on. And just if you walk up the stairs, you could follow the entire geological history. And so that is something that I am missing in this new building.
Can't we put down any Easter eggs to make it more, like put a fossil here, put a fossil
Those
there?
paintings are around still.
Yeah, so and there are discussions of, let's say, changing now, because let's say after we are now in the new building for quite a number of years, then often I think the architect becomes, he cares less. So then maybe we are allowed to do these things. But I think that's the atmosphere of the institute. If you cannot recognize it's a geological institute and with physical geography and so on, that should be visible, in my opinion. But yeah.
Question, if that's all right.
Yeah.
I was wondering, do you think that the motivation of people to study earth sciences or other climate sciences have changed now compared to when you started?
Yeah, so there is a change in, let's say, attitude. So what I always liked was the attitude of our own students, that they liked camping, like in Aliaga, there was no problem. And that is becoming less, but I think that is just a generational change. And so instead of camping, you want to, what is the name? Clamping? And everything should be well organized. So, and that's also, I think it's not good, because let's say we just got a message, okay, the 11th of June, you have to be there in that square in this small Italian village. And just see how you arrive there at 1 o'clock in the afternoon. So you bought a second-hand car or went by train or whatever, but you had to organize it yourself. And now everything is arranged. They don't have to do anything themselves. Yeah, and then I'm not sure whether you become an adult in that way. but so it is. It's not. In that respect, it is changing. But of course, the students now, so they have to learn much more different subjects than we had at the time.
Yeah, so that brings us to another little bit of a sad topic, because when you started studying earth science, how many earth science departments were around in the Netherlands? Perhaps 5 or 6?
Yeah, so when I started in 1976, we moved to the Uithof in 1978, but that was then a combination with Delft, because Leiden, they came to Utrecht. Right. And Groningen also came partly to Utrecht and was also reduced. Yeah, now we have the problem with the VU in Amsterdam, so it looks like that we may be the only geological institute in the Netherlands. And I think that's not a good idea, because I think you always need at least 2, otherwise you don't have competition. That sounds negative, but for me that's always positive.
Yeah, what is the danger and the implication of that, do you think? Like if in a more broad sense?
Yeah, so if you're the only institute, then you can just do what you want. And so, I think it's very important to have a second institute, also for collaboration. So, for instance, one of the things that people were very amazed by, that we worked together with geophysicists in Utrecht, but it was the paleomagnetic lab. It was very logical because we needed the collaboration to solve our research questions. And then later we collaborated with the Argon laboratory in Amsterdam with Jan Wijbrands and later Claudia. And so this collaboration was completely logical. And so you need to have that expertise in the Netherlands. You can of course collaborate with people abroad, but it's very good to have this expertise in the Netherlands. And if you have just one research institute left, that goes to the expense of the expertise. Yeah.
What do you think about then, if we all get into one institute, what will happen with the quality of our lectures and maybe other things? Because we would have maybe more professors teaching us how to do it.
So the question is, what is exactly going to happen, of course. So that would be decided, at least to get an idea, this month, I think, for the people at the VU. So I'm not going to speculate, also not maybe what I know about what's happening. But the number of earth scientists working in the academia will be reduced in that case. And so you lose expertise in the Netherlands. And I think expertise about Earth history, especially related to climate, but just the history of our planet, it's something that we should be interested in as mankind. So for me, I think it's a wrong shift.
So Frits, I'm going to ask you 2 cheeky but deep questions. The first is, obviously, a lot of us, we've either studied or are studying geosciences, and the job market seems to be very saturated at the moment. Are we mistaken in thinking that maybe it was easier to land work at your time?
Yeah, so that I totally, let's say, also at our time, if you want to continue in academia, that is something else than the job market. It was also not easy in our time, because the number of jobs was less. And so I think just as nowadays, it's because our students are well trained, so they can, I think, still relatively easy find a job outside academia. But what I'm concerned about, we train our students, at least that some of the best students can continue in earth sciences, and that is problematical because you have this trajectory, I call it a rat race. You do your PhD, then you enter a first postdoc, maybe another postdoc, you have to write research proposals, you have to be successful, and at the end there is no guarantee that you will get a job. And that can be some of the very best, brightest students, and I think there the system is wrong.
How would you change it?
No, at least that so that is the number of jobs that will be available in the academia to, let's say, get it in balance with the people that continue, the students that want to continue in the academia. So now there is a disbalance because And I can imagine a lot of our students, I think 30% of our students or even more continue with a PhD. And that is because they like it, they like science. But then the chance to really continue and get a job at the end in the academia, that is rather difficult.
Do you think maybe more public funding, because the money has to come from somewhere? So if people were more aware of the kind of issues that you're speaking about, maybe there's more chances for more funding, more PhDs, more opportunity.
I'm not sure whether we should really increase the number of PhDs, because we also have to look at the quality of our research and the relevance. So that is a very, I would say, delicate balance. And so just to increase that is maybe not, I would say, the best solution. But you need to get it more into balance, that people, the best ones that want to continue in science, that they can continue in science and know that at the end, after 10 years, that they will have a permanent position. Because otherwise you have these rat races and you never know whether you will get a permanent position in the academia. But that was the same in our time, so that did not change fundamentally.
If you would recommend us one place on Earth to see the Milankovitch cycli in rocks, where would you take us?
So that is one of the reasons to write this book for a broader audience. But still, one of the nicest places is where I did my PhD, is the south coast of Sicily. So that is really beautiful. We work there so often with, especially also with Wout, and so that's an amazing place. And so I made sure that the standard Geological Time Scale 2012, if you look at the front cover, that are the outcrops of southern Sicily.
That place.
Yeah, and the other one that, so there are more, but what I also liked with Margriet, when we went down in Joffre Gorge in the Caraïni National Park with the Banded Iron Formation, you go down in the gorge and then you see these beautiful cycles because you have the waterfalls, it's perfectly clean. And then, so it was such a surprising moment, because let's say if you go to southern Sicily, you have what we call quadruplets. So it's not gray-white, it's gray, white, beige, white. So you have this repetition of 4 layers per precession cycle 120 times. And these 2 white layers contain more limestone. And so that has to do with also redox, changes in redox conditions. And I have never seen these quadruplets, I've only seen them in the Mediterranean, until I went down with Margriet in the Joffre Gorge, precession-related cycles of 2.5 billion years ago, 2 white bands per cycle that we called the tram rails. And these are also redox cycles, but as you see them, you knew it directly.
All right, so Frits, thank you very much for joining us for this interview. Truly a wealth of information, and I would say one of the last real naturalist geologists out there. May there be a bright future. There has been a couple of sad, let's say a little bit pessimistic notes, but I'm sure that that everything will be okay, and that there's maybe a lot more Milankovitch cycles to come.
So it's very nice to work now together with what I call the young dogs. They were first postdocs in cyclostratigraphy, and that is the coming generation on cyclostratigraphy, and they are doing an excellent job. And some of them, but also some of our students, what I like very much, are still very interested to do field work. And that's my main hope, that we keep this field work really alive in our educational program.